Okay, we're at section 17. It's the final session before cumulative review. So let's go 17. So again, the structure of the notes is pretty simple. At least I believe they're simple. We give you a short lecture. We go through examples. Hopefully you go back and study the material that we present to you, both the lecture and the examples. You study that material, and then you move on to doing the supplemental exercises that are in the notes. Every section is almost identical. All right, after you do all that, you do the web assignment. The web assignment should seem very simple once all this stuff is completed. So what we're going to do today is we'll go through this section over here in the binomial expansion. Just to point out what a binomial is, it's two-termed expression raised to an nth power. The n over here is going to be a positive integer. My claim there's a simple pattern to it, and you want to be able to recognize the pattern. How do you recognize the pattern? By doing things. Like, for example, what you've done in Math 086, 092, 100, 119, you probably should start seeing patterns. At least we hope you do. Of course, we'll present the patterns to you that you should know about, and that's like, excuse me, a plus b to the 0 power, a plus b to the first power. You should be able to expand those out pretty quickly. Certainly when you get to 4, you might say, oh, it takes me effort. You got to put effort in. That's the key here. You got to put effort in. Of course, if you can get through this over here, then you start saying to yourself, I wonder what this one would look like. I'd hate to do it by hand, but again, if you looked at this pattern over here, my understanding is you probably could get that with the exception of the coefficients. Coefficients are tough. Like, for example, K1, K2, K3, K4, K5, K6. We'll go through it though, all right? We'll talk about a pattern to it. We'll also talk about how to compute it using arithmetic, all right? We'll also talk about a formula for Binaural Theorem. The deal about this is we go one stage at a time. I'm going to move to the whiteboard now. All right, let me a moment to do so. Give it a second to warm up. All right, you see my whiteboard. So again, I want to point out what we just talked about was we're in the section 17 of the notes. My hope is that you're willing and able to move forward. And we're going to talk about the Binomial Theorem now. All right. So again, after you go through the notes, section 17 of the notes, that is lecture, me giving examples, you doing examples, then you do the web assign. All right. Also, weekly discussion group. You know, if you can contribute something, that would be really nice. And next page. And we'll start talking about this. All right. My claim over here, again, it's a claim. I'm not saying it's, a well understood claim at this point, but if you've been paying attention throughout your educational careers, you should start to realize you've done an awful lot of expansion of binomials, all right? An awful lot of them, all right? So my claim over here is if you've done a lot of them, you can continue to do more. So for example, a plus b to the 0 is just the number 1. The only reason we put that down, I'm not going to say it's a positive integer, but the reason we put down, we want to get a pattern, right? A plus b to the first power is just a plus b. Certainly pretty reasonable, it's not difficult. A plus b squared is a squared plus 2ab plus b squared. Now granted, over here you might say this takes me effort to do this, and I'm not saying it doesn't, but you should be able to do it by hand. And this may take you effort, the 4th power, but nonetheless you'll be able to do it. So I'm gonna claim there's a pattern to this. All right, let me talk about the pattern. Right, I'm going to talk about the letters in the problem. And so, for example, 0, there's no A's or B's in the problem, right? Just the number 1. If I have 1, what am I noticing? A, B. If I have a 2, a square, what do I notice? Well, this is where the pattern really kind of emerges for me. I'm noticing there's A squared, A, and then no A's over here. And the B's, what am I noticing? Well, if I looked at that, I would say, there's no B's, 1B, 2B. All right, let's do the next one. Well, I'm looking at the pattern of the A's. A cubed, A squared, A, no A's. And if you're looking at the B's, I'm going to go backward this time. B cubed, B squared, B1, B none. Let's go to the next one. A4, A3, A2, A1, A none. If you want B's backwards, B4, B3, B2, B1, B none. So I'm going to claim there's a pattern here. And let's go through the pattern again. If you had the nth pattern, the nth exponent over here, and I just did the a's, you'd have an. What would the next one be? Well, I go down one, right? I hope you realize we just did that with integers. Now I'm just saying n's an integer. We go down one, then we go down another one. So it'll be an minus 1, an minus 2, then you get an minus 3. I hope you realize you'd eventually get down to a squared, a1, and then a none. Let's go b's now. Well, we're going backwards now. bn minus 1, bn minus 2. Eventually, we're going to work her back up, way up, b cubed, b squared, b, and then no b's. I do want to point out there's a pattern to this, and you should recognize that pattern. The other pattern I notice is the sum of the exponents in every single case turns out to be n. All right, let me check that off for you. Well, there's only one exponent there, that sums to n. There's two exponents here, n minus 1 and 1, that sums to n minus 2 and 2 sums to n minus 3 and 3 sums to n, 2 and n minus 1 sums to n, 1 and n minus 1 sums to n, and certainly n is n. And that's true with the other ones we just did too. If you look at every single term, the sum of the exponents sums to these things. Right? So I'm going to say it's a pretty easy pattern. So for example, if you put a plus b to the 7th, let me point out where we are. I could clearly put down the a's. Let me go through that with you. A7, A6, A5, A4, A3, A2, A1, A none. And I could clearly put the b's down. B7, B6, B5, B4, B3, B2, B1, B none. What I can't do, and this is the problem for me, I can't readily put down the coefficients. And this is going to be a struggle, and let's talk about the struggle now. To do the struggle, I want to write a triangle down for you. And someone says, why are you putting a triangle down? I'm not putting a physical triangle down, I'm putting a numerical triangle down. So looking at this business over here, I'm going to write the triangle I'm seeing. Well, the first guy gives me the number 1. I'm just writing coefficients down. The second guy gives me 2 coefficients, 1 and 1. The third guy gives me 3 coefficients, 1, 2, 1. Well, let's see, let's see, 1, 2, I'm on the 4th one, right? What do I get over there? 1, 3, 3, 1. I'm just writing the coefficients down. Let's put the next one down. What do I get? 1, I'm just reading it, 4, 6, 4, 1. What I could do is I could generate the next row by expanding a plus b to the 5th power. But I want to see if there's a pattern to it. And I'm going to look at it. And what I've noticed over here is 1 entry, 2 entries, 3 entries, 4 entries, 5 entries. This would have 6 entries. So a plus b to the 5th power would have 6 coefficients. What do I notice? Along this edge over here, it always appears to be popping up to be a 1. I'll write that down for you. And this thing over here, it always appears to be a coefficient of 1. All right, let's do the next one. I'm looking for patterns. 1, 2, 3, 4. I bet that's 5. All right, put another one down. 1, 2, 3, 4. I bet that would be 5. By the way, betting doesn't mean it's right. All right, I got trouble now. But I want to point out, I think I see another pattern. I'm going to point it out to you. It looks like this 2 here is the sum of those 2 prior entries. And it looks like this 3 over here is the sum of those 2 prior entries. This 3, sum of those 2 prior entries. 1 plus 3 is 4, 3 plus 3 is 6, 3 plus 1 is 4. 1 plus 4 is 5. 4 plus 1 is 5. I think I could put that one down. 4 plus 6 is 10. And 6 plus 4 is 10. All right. I could keep doing this all day long, but I'll be honest with you, it gets nasty quick. So I want to write down a plus b to the fifth power. And I'm going to write the a's down first. A5, A4, A3, A2, A1, A none. And then I'm going to write the b's down in opposite order. B5, B4, B3, B2, B1, B none. Now I'm going to write their coefficients down. And where are they coming from? Over here. 1 plus 5 plus 10 plus 10 plus 5 plus 1. I'm going to clean it up. What would I get over there? A5 plus 5A4B plus 10A cubed B squared plus 10A squared B cubed plus 5AB4 plus B5. I was going to say, I wonder if that's right. Well, what you could do is this. You could do a plus b to the fifth power, a plus b times a plus b times a plus b times a plus b times a plus b. Let's see, 1, 2, 3, 4. Yep, I got that. I could multiply this out pretty easily, right? A squared plus 2ab plus b squared. Whoops. I can multiply that out. That gives me a squared plus 2ab plus b squared. And yeah, the last guy would be, wow, this looks like way too much work. I don't want to do that. I'm going to erase that. Like way too much work for me. I'm not saying too much for work. You obviously say too much work for me. I'm going to use a tool. And I want to see what tool would do that for me. And what I want to do is I'm going to switch screens again. And I'm going to go to Sage. Give me 1 second to do so. Make sure you have notes, by the way, because otherwise you're not looking at my notes anymore. You're looking at my computer screen now. And let me go back to Sage. And I'm going to say reset. I think we've done this many times before. A, B, I want to make them variables. And so A is a variable. And B is a variable. Whoops. And what I want to do is expand. And I want to see if I got the right answer. I said A plus B to the fifth power. I got my notes in front of me, by the way, and you should have your notes ready as well. And I want to see what it gives me. I'm looking at my notes now. I'm going to get my red pen out, and I got to grade it and see how good I did with my pattern recognition skills. So let's take a look. It says the first term is A5. I got that. What's the next term going to be? 5A4B. All right, I'm getting my red pen out. 10A cubed B squared. 10A squared B cubed. 5AB4 and B5. All right, I'm going to go back to my whiteboard and give me 1 second to do so. Okay, I got it right. My pattern recognition, at least we're good for A5. I mean, N equals 5. And I did A plus B, all right? So I'm going to point out to you that we could prove this, right? Which may be a little difficult, but we could prove this by the principle of mathematical induction. All right, we could prove it for any n. All right, why is that? It really lends itself nicely to that. Now, what I want to do is I want to talk about what these coefficients really mean to me. All right, so I'm going to go back over here and I'm going to talk about the meaning of these things, to me anyway. So I'm going to just, focus in on this guy right over here. And what I'm going to claim over here is the 5 is the number of orderings of those letters. And what are those letters? A4, which is A, and there's one B. Now, I'm going to claim there's 5 orderings of that. In other words, 5 distinct words. Now, when I say words, I'm not saying you could pronounce these words, but they are words nonetheless. All right? I've got 3 already, don't I? And last but not least, whoops, would be B followed by 4 A's. All right, what did I notice? I got 5 orderings of that. Now, not that I want to do it, but if you did A cubed, B squared, what you're going to find out, there's 10 distinct words for that. I mean, you could write another one down if you wanted to, like BB, A. I don't want to write all 10 down. You get bored people. A, B, B, A. That's another one. But you get 10 distinct words, all right? Now, I need a better way of doing it, though. And what I'm going to talk about is that there's a way to compute a binomial coefficient, all right? There's a way to compute a binomial coefficient. Now, before I do that, though, I want to point out some students just want to generate the table, all right? So what I want to do is I'm going to take this thing here. Whoops, I didn't do a good job there, did I? I'm going to grab this thing here. And I'm going to make it longer. All right, I'm going to make this longer. I want to get to 7. And then we'll talk about how to compute those. I do not like using this triangle, but this triangle has a name, and the name of this triangle is Pascal's triangle. Let's generate the next row. What's it going to be? 1, 6, because 1 plus 5 is 6. 15, because 5 and 10 is 15. 10 plus 10 is 20. 15, 6, and 1. You should notice a lot of symmetry to this work over here. That left to right, these things are palindrome. Right to left, a palindrome. All right, let's do the next one. 1, 7, 21, 35, 35, 21, 7, and 1. I want to concentrate on this one right over here. How many terms are there? Let's count it up. 1, 2, 3, 4, 5, 6, 7, 8. What does this correspond to? A plus B to the 7th power. This will have 8 terms. Let's write them down now. All right. Now, when I write them down, it might look strange to you, but I'll put A7, A6, A5, A4, A3, A2, A1, A none. B7, B6, B5, B4, B3, B2, B1, B none. Let's put the coefficients down. 1, 7, 21, 35, 35, 21, 7, and 1. Now, someone says, I want to leave it that way. I don't think it's a good idea. I really think you should simplify this. What do you get? A7 plus 7 A6B plus 21 A5 B squared plus 35 A4 B cubed. I got to push that over. So you lost the coefficients. Not really. It's a pattern. Plus 35 A3 B4 plus 21. It's a palindrome. Pretty easy to read, right? When I said the numbers are palindromic, what do you get? A2 B5 plus 7, A, B6, whoa, whoops, sorry about that, plus B7. All right, let me do over here. I'm going to say, I believe that's the correct answer. We'll check it in Sage in a moment. Before I move on, though, I want to point out some of the exponents 7, 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 7. Where to get these coefficients from? Pascal's triangle. What I'm going to do now, though, is I'm going to see, did I get it right? I'm going to go back to Sage. I want to see if I did a good job. And I'm going to type it in for you now. You're looking at my Sage screen. I want to type in expand. And I want to expand A plus B to the 7th power. And I got my red pen. Whoops, I made a mistake there. I got my red pen out. And who knows, maybe I made a mistake. Maybe my patterns aren't really correct. So let's take a look at it. And when I look at it, I'm going to look at one term at a time. I'm looking at my whiteboard, though you're not looking at that. I'm looking at the Sage now and my whiteboard. A7, you should have notes as well. 7A6B, 21A5B squared, 35A4B cubed, 35A cubed B4, 21A squared B5. Oh boy, 7AB6 and B7. I got every term right. You might say it's a miracle. Maybe it is. All right, maybe it is. Let's go back. I'm going to go back, do another share. I want to go back to the notes on my whiteboard. All right, so I got all those terms right. All of them, every single one. And I could play this game for a long, long time. My issues, though, is Pascal's triangle becomes incredibly difficult to do when you get higher ends. Like you might say, well, what happens if you get 12 or so? Well, I need a way to compute this, right? I need a way to compute these numbers over here. And I'm going to tell you there's a formula for it. Let me go back over here. And for you guys taking discrete mathematics, maybe your teachers talk about this, maybe not. I'm not sure what they're talking about in discrete, but they should be talking about this because it's really a discrete problem. It's a number of orderings of something. And these are going to be the orderings. All right, so I'm going to put this over here. Now, it also has different meaning, but right now I'm going to say it's orderings. This is orderings. All right, so someone says, how does it relate to those problems over there? And I'm going to go through it with you. So I'm going to write this over here. Look at this over here. I'm going to pick one of these terms. And the term I want to pick is I'm going to outline for it. I want to pick this term here. And I want to compute the coefficient of 35. I'll write this down for you. So they claim it has something to do with the formula n, and then there's an r here. And this is a computational problem. It's n factorial. Yes, we've seen that before. And the bottom would be r factorial times n minus r factorial. So let's go through it for this guy right over here. All right, I'm going to write this down for you. And I'm going to say, what's the n in the problem? Well, I hope you realize it's 7, which is just some of the exponents. Then the question comes is, what's the r? It's either the number of a's, which is 3, or it's the number of b's, which is 4. I claim they'll give me the same answer. Let's go through the arithmetic. And yes, you have to be able to compute that. Let's write this down. The first guy is 7 factorial, 3 factorial. Now 7 minus 3 is 4 factorial. What do you get over there? 7 factorial, 4 factorial, 7 minus 4 is 3 factorial. Let's do the arithmetic. You get 7 times 6 times 5 times 4 times 3 times 2 times 1. I'm really not interested in doing that, by the way. The bottom is 3 times 2 times 1, and then 4 factorial, which is 4 times 3 times 2 times 1. Let's do the other side. A lot of writing, though, isn't it? 7, 6, 5, 4, 3, 2, 1. 4 factorial is 4, 3, 2, 1. And 3 factorial is 3, 2, 1. Get my red pen out, cancel things off. Let's see, 4, 3, 2, 1. That cancels off. 3 times 2 is 6. That cancels off. And what are you left off on? 35. All right, let's do the other one, see what happens over there. Well, let's see, 3 times 2 times 1 cancels off, 4 cancels off, 3 times 2, 1 is 6, and 7 times 5 is 35. No surprise there. Why is that? We said it was going to be 35. All right, we said it was going to be 35. All right, let's take a look at another example. And I'm going to do this one over here. All right, we'll talk about it. All right, so I'm going to write this over here. It can be written as, let's write this down, 12C 7. That could be written as 12. Well, let's see, if there's 7 A's, how many B's would there be? 5, right? Or it could be written as 12 7. Or it could be written as 12 5. I'm going to do the computations, and I'm going to do one at a time. 12 factorial. And what do you get on bottom? 7 factorial. And let's see, 12 minus 7 is 5, right? Now again, I'm going to claim this is the same thing as this. Well, let's see if that's true. You get 12 factorial on top. That's certainly true. Then you get 5 factorial, and 12 minus 5 is certainly true. Let's go through the computation now. And it's not going to be easy. All right, let's put this one over here. So 12 factorial over 7 factorial, 5 factorial. 12 times 11, 10, 9, 8, 7 factorial. Someone says, why'd you stop at 7 factorial? I got one at the bottom, that's why. Now what's 5 factorial? It's 5 times 4 times 3 times 2 times 1. I'm going to do some cancellations. Whatever that number is, it cancels. 7 factorial divided by 7 factorial is 1. 4 times 3 is 12. That cancels. 5 times 2 is 10. That cancels. So what am I left off with? Let's write this down. You left off with 11. And then you left off with 9. And you left off with 8. Now, I'm going to go through the arithmetic with you. And the way I do arithmetic might be a little bit different than you, but the outcomes can't be different. I'm going to do 11. And then I'm going to say 9 times 8 is 72. I make mistakes all the time, by the way. 10 times 72 is 720. And 1 times 72 is 72. 720 and 72 is 792. Let's look at the thing. Wow, we got it right. So what am I saying over there? If I had a binomial expansion, a plus b to the 12th power, and I would expand that, I would eventually get to a term that would have this in it, a7, b5. I'd eventually get there. Then the question comes is, how many orders would that be? I would hate to put that down for you, but there's 792. All right. I want to go back to Sage, and I want to show you a few other things in Sage. Again, why we should pointing out Sage, you probably should learn how to use a computer. Yeah. New share, desktop. And what I'm going to do is go back to Sage. And I'm going to scroll over here. And I want to do this thing over here. All right. So someone said, how would you do that? Well, most people would say, I bet I could put 12 factorial down. Unfortunately, Sage is going to balk at that. You see, it says something weird with that. So I'm going to clear it. That can't be right. So I'm going to just do FAC. Maybe it's the word factorial. And hit the tab completion. Tab completion is going to take the thing and wonder, is there any command that looks like that? And there's 2. Which one do I want factorial? You see that? I want 12 factorial. Divide factorial. Seven. Divide by factorial. 5. We just did the computation, right? 792. as expected. One thing I want to tell you, another thing, I'm going to do tab completion, binomial, and I'm seeing it. I'm seeing the binomial coefficients right now. So I'm going to type in 12. I want to show you what happens. It gives them all to me. Pascal's triangle. 1, 12, 66, 220, 495, 792, blah, blah, blah. Let's take a look at this. Which one is this? 5, 7. Well, it's right up there, isn't it? 792 or 7, 5. Right, you get the idea? 5, 7, 7, 5. It's really the same thing. 792. All right, 792. All right, let me just take a look. I want to look at that, make sure you're okay with that. You got 5, 7, 7, 5. It's both 792. We expected that. All right, so I'm going to say one other thing, we got to get back to the notes. I want to make sure you can follow along what we're doing. We'll go through examples later. Let me do another screen share with you. Let my whiteboard warm up a little bit. All right, so I'm going to go back. Oops, right over here. So we just covered that binomial coefficient business over there. All right, let's go to the next page. And just one other topic over here. The way we like to write things down maybe vary from student to student. You should learn how to write some things down, of course. But I want to emphasize over here that this form over here, give me 1 second. Let me get my eraser out. Did a doohickey over here. This form over here is really the form we'd like to write things down. It's really compact. I'm going to expand it for you. And you should know about some formats at this point. And let's write this down over here. N0, that's where we're starting. A to the N, B0, plus N1, A to the N minus 1, times B to the first power, plus N2, A to the N minus 2, B2. I'm getting tired. This is eventually going to come down to, and I'll write this over here. Well, we're going to get close to N at some point, so I'll put down N minus 1, A. What will we get over there? Again, if you can't remember, look at it. It's N minus R, right? So N minus N plus 1, which is A to the 1. And then we go over here, B to the N minus 1. Remember, the sum of the exponents is always going to be N. All right, last but not least, let's write this over here. NN, A0, B to the N. All right. Again, we like to do that. You may have to think about that. All right. Next up, we'll do the examples. We'll work through all the examples for you at the whiteboard. And then after that, you say, so what am I going to get to try? After we do the examples, you can retry those examples, but then we have new examples for you to try. All right. Thank you.